Okay, so last class we talked about redox reactions. And let's go over here and let's draw a redox table because we are going to add to it today. And my redox tables will usually have 5 or 6 rows here with these 2 columns. And when I say redox, we're going to try and organize information we know about reduction and oxidation reactions, half reactions. So some reactions, not all, can involve the gain and loss of electrons. Now remember, Leo the lion says grr. So Leo, the loss of electrons, oxidation. So oxidation is the loss of electrons. And then Leo says grr, the gain of electrons. We can get that. Leo says grr. The loss of electrons is oxidation, the gain of electrons is reduction. So we can get our redox table started off like this. So again, why is it weird that the word reduction is tied to the word gain? That would be weird except for the fact that electrons are negatively charged. When you gain these negative particles, you kind of like your oxidation state would be going down, so it's being reduced. So now I like to get another column, and I always like to draw this arrow just to help me visualize what's going on. These things are losing electrons to these things. So we have electrons being transferred here. Now the thing that I'd like to add today to our redox table is this. Redox reactions can be broken down into 2 separate reactions, really. The reduction half reaction and the oxidation half reaction. If you have something being reduced, you have to have something being oxidized. So I'm going to get 2 little mini arrows here to show the reaction, like A turning into B or whatever. And if electrons are being gained, that means they are going to be found on the reactant side of the half reaction. And we're going to practice doing this in a little bit, but I just want to have this here on this table. And since we can have open notes here, we can remind ourselves that the reduction half reaction will always have the electrons on the left side of the arrow, on the reactant side of the reaction. That means that when electrons are being lost, they would be found on the product side of the half reaction, or the product side of the reaction. Okay, this is all we're going to do, adding to our redox table for today. And now let's jump over here, and I want to practice separating a reaction down into a half reaction. So let's say I had this fake reaction between A and B reacting to form, so these would be element A and element B, and let's just say we have 1 atom of each, combining to form ionic compound AB. And notice how, I kind of have my coefficients balanced here, I suppose. So what would the oxidation state of A be if it's an element? Not AB, but what would the oxidation state of this be? Okay, it'd be 0 because it's an element. What about the B over here? The B would also be 0 because it's an element. Now if this were an ionic compound, how would we guess what this is? Well, the oxidation states of ions that make up the ionic compound are just the same as the charge. So that means A would be a +1 and B would be a -1. Now, is something going up? Well, yeah, the A is going from 0 to +1. So the thing going up, is being oxidized. So going over to our redox table here, that means the A would be losing electrons. It's losing an electron to become oxidized. Okay, the B is going from a 0 to a -1. That's going down. So the B is being reduced in this reaction, which means the B is gaining electrons. Now, this is the overall reaction, but we can separate this down into half reactions, and this is how we do it. Just start with, whatever you want, really. I'm just going to start with the A. So essentially, the A is turning into A+, because that's the ion found in AB. So now look over at your redox table. The thing being oxidized, where would the electron be found? Okay, it's on the right side. This is really just our check, or how to check our work. Here's what I want you to understand. In half reactions, atoms must be balanced. That's kind of old news. We've practiced that all year. So I have 1A here and I have 1A here. Now the new idea is that the charges must also be balanced. And the only way we can adjust charge is by adding negatively charged electrons. So What's the overall charge on this side? 0. What's the overall charge on this side? Plus 1. You will always add electrons to the higher side. So I'm going to add 1 electron here because 0 equals plus 1 plus negative 1. Does this correspond with my table? Yes, the oxidation thing has the electron, the oxidation half reaction has the electron found on the product side. Now what's the other half reaction? Oops, you can label this as the oxidation. So my B atom is turning into a B ion, B minus 1. Okay, now I have 1 atom of B here, I have 1 ion or 1 B on the product side, so my atoms are balanced. But what about my charge? This is a 0 and this is a negative 1. That's not balanced. Now what's higher, 0 or negative 1? 0's higher. The electrons will always go on the side with the higher oxidation states. So I would now put my electron right here, which also corresponds with my redox table that says the reduction half reaction will always have the electrons found on the left side. Okay, now, and now you see I have a negative 1 on the left and I have a negative 1 on the right. Now my charges are also balanced. Now, what we need to make sure is that when we're done here, this number of electrons has to correspond with this number of electrons because the electrons being lost need to be the same as the electrons being gained. Okay, let's do some practice problems for this. So just separate these into half reactions. So I have zinc reacting with copper ions to form zinc ions and copper. Let's start by doing the oxidation states to help us visualize the oxidation reduction. So the zinc element would be 0, copper plus 2 is plus 2, zinc plus 2 is plus 2, and the copper element now is 0. So what's going up here? It looks like the zinc is going from 0 to plus 2, so I'm going to write that as my oxidation half reaction. The oxidation will always be going up. Okay, I have 1 zinc here, 1 zinc here. My overall charge on this side is 0. My overall charge on this side is plus 2, so I'm going to add an electron to this side. Oh, wait. This side is now 0, and this side is now plus 1. That's not okay. So we got to make this 2 electrons. So this zinc atom is essentially losing 2 electrons as it's being oxidized. So now the charges and the atoms are balanced. So the reduction half reaction then would be copper ions turning into copper. This side is plus 2, this side is 0. I would have to add the electrons to the reactant side now. And then how many? Well, if this is a plus 2 and this is 0, I would have to have 2 electrons to this side. And then check this out. These two numbers match. This reaction has the zinc being oxidized and the copper ions being reduced. And we have 2 electrons being transferred here. Okay, what about this question? We have aluminum plus Ag plus. The aluminum is a 0. The Ag is a plus 1. The aluminum is a plus 3. And the Ag is a 0. Okay, the aluminum is going up, so it is being oxidized. Okay, for this problem, the higher value is over here. This is a plus 3, so I would need to add 3 electrons to the product side. And I have Ag plus turning into Ag solid. This side is the higher side. It's got a plus 1, so I'm going to add 1 electron to this side. Now, is this possible to lose 3 electrons and to gain 1? That is not possible. So now we need to multiply all of these by a 3 technically. So now we have 3 silver ions gaining 3 electrons in total to form 3 silver atoms, and they're gaining those 3 electrons from the 1 aluminum that's being oxidized. So now these numbers match, and now I got my half reactions. Now if you were to look at this half reaction on its own, you might see it simplified, but when we look at them together, we kind of want to see these electrons match. Okay, what about the next problem? 2H plus zinc forms zinc plus 2 and H2. Okay, so it looks like my H is a plus 1, my zinc atom is a 0, because it's an element, My zinc ions are +2, and my H2 is a 0. Okay, so what's going up? My zinc's going up. Zn turning into Zn +2. That means I would have 2 electrons found over here. And I have 2 H pluses going down to form an H2. You know, I have 2 H's and I have 2 H's. So since this is the higher side, I have 2 H pluses here, so I need to add 2 electrons to the left side, the reactant side. And these numbers of electrons do match, so we're good. Down below, I have fluorine reacting with lithium to form ions. So these are elements, so they are both 0. Li is a +1, F is a -1. What's going up? Well, the lithium's going up from Li to Li+. So I would have 1 electron on the right. What's going down? The fluorine is going down from 0 to -1. So this time I would have to put, well, wait a minute, oh, see, this is a 0 and this is a 2- on this side, so I need to add a 2- on this side. Now the charges are balanced. So you don't always add the electrons to the side that has a positive, maybe. You just add it to the higher, and 0 is higher than -1. Now, do these electrons match? No, they don't. So we need to multiply all of these coefficients by 2 technically. So the electrons being lost equals the electrons being gained. Okay, 3 more. Separate this reaction into a half reaction. So zinc reacting with HCl to form zinc chloride and hydrogen. Zinc atoms are 0. H is a +1, which makes these chlorines -1s. This zinc and zinc chloride, this is an ionic compound. Ionic compounds are made up of ions. Chlorines are always -1 when they're in ionic compounds, so that means this 1 zinc would be a +2. Hydrogen is an element, so it's 0. Now, what's being oxidized? What's going up? Well, the zinc is turning into zinc chloride. Now, you can kind of get rid of the chlorine out of this because it's not really taking part in this. Because we need to look at the zinc turning into a zinc +2. Wait, this looks awfully familiar to... Oh, look, check that out. I was just showing you how in this problem I kind of just got rid of the chlorine ions because they're not really taking part in the oxidation reduction kind of aspect of this reaction. Just showing you how we can do this same reaction 2 different ways. So the electrons are found on the right, and I have 2 H pluses being reduced into H2 molecules. This time the left side's my higher, so I would add 2 electrons to this side, and my electrons are balanced, so we're good here now. What about in combustion of hydrogen gas that we read about in that 16.1 chapter? Well, what's going on here, why this is a redox reaction, is because these elements would have oxidation states of zeros, and then the compound water, hydrogens are +1, the oxygen's a -2. So it looks like we have something going up and something going down. Well, this is kind of a goofy one to separate into half reactions, but we'll try. So we have 2 H2s here. And this one I already balanced for us to kind of help us out. So these are really H pluses, and how many of them do I have? Well, what's 2 times 2? It's kind of into 4 H pluses. So this side has 4 H plus, so I would need to add 4 electrons to this side. Down here for the reduction half reaction, I have an O2 molecule. So I have O2 minus kind of ions here, and I have 2 of them. So 2 O minus 2s. Now what's 2 times -2? I'm trying to show you some little trickier examples here. 2 times -2 is -4. So that means I need to add 4 electrons to this side. So now my electrons do match on my product and reactant side. Okay, this last one is a really goofy one. And I left it unbalanced for now. Try and play through this one for a minute and see what you get. And then unpause it and go through the solution here. Okay, so I would always start with oxidation states. So oxygens would be -2, always, in the examples I'm doing. So 3 times -2 is -6. This ion has a -1 total, so that means this chlorine would have to be a +5 to balance this out. Iodine element here would be 0. Over on the right side, this is a chlorine ion. It's got to be a -1 because the oxidation states of ions are their charge. And then IO3 minus. So again, oxygen is a -2. And 3 times -2 is -6. This ion has a -1 charge total. So the iodine would have an oxidation state of +5. Okay, now, this is a weird one, but just check it out. So my ClO3 is turning into Cl minus here. Notice how the oxygen isn't changing from left to right, so that's not really the thing being oxidized or reduced. So my ClO3 minus is going up to form Cl minus. Oops. Let's save that. Sorry. My iodine, I2, is forming IO3 ions. It's going from a 0 to +5. That's going up. Now, this is a little goofy, but do you see how I have 2 I's right here? That means I would have to have 2 I's right here. Okay, now, these iodines have an oxidation state of 0, and here they go to +5 each. So if these are +5 each, and there are 2 of them now, this is why this was a little trick, and I mentioned that it's unbalanced for now. 2 times 5 is 10, so we would need 10 electrons right here being lost for the iodine to go from a 0 to a +5. Okay, the reduction half reaction, we have ClO3 minus turning into Cl minus ions. Now the chlorine is going from a +5 to a -1. What's the difference between +5 and -1? Well, I guess it would be 6 electrons. Now, do you notice how the charges here are not balanced for now? Well, that's because these kind of are separated in their half reactions. So we have the chlorines gaining 6 electrons to form this. Now, this is a weird one, as I said, but we have 10 electrons here and 6 electrons here. That is not okay. Now, what is the most common number? I mean, it might look like 60, but what's the most common number between 10 and 6 would be 30. So I would multiply all of these by 3. And I would multiply all of these by 5. 5 and 5. Okay, and now we kind of balance these half reactions, and we have the same number of electrons being lost and the same number being gained. Now, how does this relate to the video we watched last class maybe? So here's my lemon, and right here I have a voltmeter. So a voltmeter can measure voltage. So check this out. If I take a little, we're rich right here. We have Lego $100 bills. So if I take this Lego $100 bill and stick it in this lemon, and I take this little Dilophosaurus dinosaur and stick its tail in there, and then I touch my electrodes, oh wait, yeah, that doesn't do anything. Okay, but what if I take this zinc nail and this copper penny, and I put them in this lemon here? So this zinc and this copper, they like to react with one another because one of these would like to lose the electrons and one of them would like to gain them. And as long as that's possible, we can have a reaction produce a voltage here. So if you can see my voltmeter, this nail and this copper penny are causing electrons to flow because it's a redox reaction. Now, next class, we're going to talk more about the purpose of the lemon here. And you can see that it's creating a voltage here, which is really just a measure of electron flow. And if I took another lemon with a zinc nail and a copper penny in it, and then I got a wire, and I connected this penny to this nail, you could see that my voltage now, instead of being like 0.46, we got like 0.98. You know, it can essentially create even more voltage by adding those two voltages together. And what's going on is we have these little half reactions where one of these things is gaining electrons and one of the things is losing electrons. So I just wanted to show you how I could do this little fruit battery at home also. And this is what we will be doing next class, is explaining more how batteries work using half reactions. Okay, great job today, and let's keep it up. We're almost done.